Okay. Yeah. So, well, when you talk about this, the what we call the yeah. So when there would be a non-linearity, that is abrupt changes, right? So the flow will become no longer a linear because of this abruptness. The properties will become a non-linear structure. So such a phenomena is what we call a turbulence modeling analysis. So you see that whenever you are wind changes its direction and also longitude as well as altitude, there will be a disturbances. That density, that is nothing but Ti is sigma u upon u bar, where sigma u is a standard deviation. How actually it is deviating statistical properties, you call it as a first moment, you call it as a second moment, you call it as a third moment. The higher the moments, the better will be the approximations. And in terms of the spectral density, there is a chimal spectral density, especially for the normalized power sectors. We use n times of SUN upon sigma square u, where sigma is the standard deviation, S is the sum of all the points 1, 2, 3, 4, 5 like that. Then you approximate it with the normal frequencies. So that means there would be since it is a waves of different amplitudes, waves of different frequencies, so there will be a what we call dissipation, there will be a dispersion. So therefore dissipation is not just because of the diffusivity, just because of the moment of the particles, how they bombarded each other. So therefore wind farm wake effects modeling, that's one of the important modeling which we use in the climate modeling, atmospheric dynamics, and even in the case of principal component analysis also. There will be a wake velocity deficit which we can compute upon delta u upon u naught, where u naught is at the initial point and u is the change with respect to the angle alpha, and ct is the thrust coefficient which we call it as, and alpha is the most important quantity which we call it as a wake decay constant. Similarly, this kind of analysis can also be done in the computational fluid dynamics modeling. And since it is a turbulence modeling, we use what we call Reynolds average Navier-Stokes equations. That means the properties of U, V, W, pressure, they will be having a highly disturbed flow modeling, which we call it as the turbulence modeling, and which also we than it using a u. So look at this equation. If you see dou u by dou t, it is the unsteady case point, and uj times of dou ui by dou xj, it is the convection part, which is basically a non-linear. Because of the moment of the bombardment of the particles, convection takes place. And there will be what we call minus 1 by rho dou p by dou x. That's the pressure gradient. Change of the pressures from one point to the another point. Then there will be nu into d square u upon dx square. There is a diffusion. So diffusion takes place, right? And the last quantity will be dou ui upon dou x of j. This is the velocity gradient. Well, there will be a wind farm layouts also when it comes to the boundary layer approximations. That is, a small movement of the fluid particle, when it close to the surface, there is a layer would be coming up. That is what is called the boundary layer. In the boundary layer, the viscous forces are more prominent as compared to the viscous inertial forces. But outside the boundary, their behavior is much different. And we try to maximize annual energy production in such a way that summation maximum of I is equal to 1 to n, j is equal to 1 to m. And if you take I is equal to 1 to n in one direction, j is equal to 1 to m in the other direction. P of V day D, that is Fi, where T is the turbine positions and Fi is the wind direction frequency. So the most important property is here wind direction, wind speed. And because of this, there would be what you call wake superpositions will take place. That is what we call linear superposition principles. So in the linear superposition principles, there will be U of deficit is nothing but U naught minus summation delta UK. So delta UK is nothing but the change over particular point, and when you take the deviations from one point to another point. There are some case studies which we already did it in recently using the physics informed neural networks. The problem specification, for example, if we have a 200 turbines, 5 megawatts each, and site is, let's say, 25 kilometers square of the kilometers offshore area. How actually the atmospheric conditions can be computed, and in the, let's say, that offshore areas, water depth, let's say 20 to 40 meters, distance of the shore is, let's say, 15 kilometers. So we'll try to see how actually the simulation can take place. Optimization results is layout is grid 3420, that is gigawatts hour per year, and capacity factor we use 39.1. And if you optimize it, then you get a better, that is up to 42% it will goes. That means there will be an improvement of 7.6% by using this process. And in fact, if you use more number of grid points, you get a better solutions. And look at this integration challenges and solutions. There are many more challenges available for trying to find out this the methodologies. One is the important factor is grid integration issues. How actually you could able to integrate the grid issues. One is the intermittency and variability. The higher the variability, the better will be the approximation. But when you go to the neighboring points, you will not be able to get the better variability. Therefore, you need to find out a discrete points at discrete locations. Similarly, voltage and frequency regulation and power quality concerns, and there will be above all, the grid stability is also very, very important. So the what that we can learn is, what we learned from this talk is how actually we could able to forecast it. The forecast is nothing but the weather predicting, and for the defense applications, the space applications, for Internet of Things, and so on and so forth. And there will be a lot of disturbances in the atmospheric sciences, and that's why the statistical properties also plays a vital role. For example, if you write the statistical properties in terms of PTH, T plus H, at time T at a distance of H, alpha naught plus alpha naught is the initial base point, and alpha I PT minus 1 and epsilon T aj minus 1. There will be what we call a change of what we call this is epsilon small change that we replace by epsilon. And there will be a primitive variables method by using how the linear momentum, linear continuity, linear thermodynamic equations takes place over the control volume. So in the momentum primitive variables, what we do is we write it as dv by dt plus 2 omega cross v is equal to minus of del p. Minus of del p is nothing but the gradient, pressure gradient, and rho g is nothing but the gravity, and f is nothing but the outer external force. So therefore, since it is a valid fluid flow, automatically it has to satisfy the continuity equation, which we call it as dou rho by dou t del dot of rho v bar is equal to 0. And for thermodynamic case, it is d theta by dt is nothing but 1 over rho Cp, that is equal to dq by dt. The scale of the motion, we can write it as planetary scales, we can write it as 10 power 10 Newton. Symptotic scales, we can write it as in terms of 10 power minus 5. Mesoscales. So therefore, these are some of the measurements how actually the motion of the can be computed by using the different scales. That's why we call it in the sea. You might be knowing what we call, there is a nautical distances. That's the word which we use it, nautical distances. Then next thing is how the global energy conservation takes place. How we could able to cope up this global energy. Rate of energy change is nothing but energy in coming into the system, and you subtract energy going out of the systems. So if you compute in terms of the enthalpy, dE by dt is nothing but S naught times of 1 minus A minus sigma times of T power 4 E, where S naught is the solar constant and A is the planetary albedo. Then with heat capacity, we can write it as C into dt by dt is equal to S naught into 1 minus A minus epsilon sigma t power 4. Well, the approximation of this numerical methods can be done by, as we spoke, there will be the point. If you go to the forward, that will be the forward difference, and if you go to the backward, it is called a backward difference. And if you take average of these two, or maybe central point of these two, which we call it as a central difference. So central difference will give you a better approximation, because you are carrying out the points at I minus 1th level, you are also carrying out the points at I plus 1th level by sitting at ith level. This is not just only the spatial discretization, there will be a temporal discretization also, one can do it. The most important the scheme is what you call leapfrog scheme, that is un plus 1 I is nothing but un minus 1 I plus 2 delta t dou ut by dou n. So it is a explicit scheme, because at n plus 1th level you are computing at n minus 1th level plus the nth level. So nth level is known, n plus n minus 1th level is known. So therefore, this, if you use semi-implicit method, so ui n plus 1, you see here n plus 1th level is on the left side and also on the right side. So this scheme will become implicit schemes. So normally, as per the the trend is concerned, or the practice is concerned, implicit methods will give you a better approximation, better forecasting, especially for the atmospheric modeling is concerned. And spectral methods in atmospheric modeling also will give a better insight, that is spherical harmonic expressions. You will have a different harmonics, that is waves of different lengths, different wavelengths, different frequencies, we transform into a harmonics. Similarly, we use transformation methods, that is the forward transmission, and at discrete points we equate it as a continuous points, therefore we replace the summation by the integration methods. The other methods which we have is what we call one box method, that is C times of dt by dt is nothing but q times of 1 minus alpha minus a minus of bt plus f. So which we call it as a equilibrium temperature equations, and there will be a response times. Two box model also can be used. C1 times of dT1 by dt is nothing but q into 1 minus alpha, where ABCD are the constants and gamma is the heat exchange coefficient, which we need to compute it. There will be a carbon cyclic matrix formulation which we use in atmospheric modeling, that is what is called the dc by dt. So because the derivatives quite often we are using, because there will be changes from one point to the another point. C is the carbon content vector and A is the exchange matrix. So in case of three dimensions
Sir, we cannot hear you.
Sir, even
Screen is not sharing, sir. Hello. Sreenivas,
is
sir.
not visible, sir.
Sreenivas, sir.
I think any power cut, it seems. Internet cut or power cut, it seems.
Just a minute, I will call.
నేను తప్పు చేస్తానని భయపడ్డానికి నువ్వు భయపడుతున్నావా అందుకే
Wait for 2 minutes. Dear all, please wait for 2 minutes.
Hello, ma'am. Vasundhara, ma'am.
Yes, sir. I called to sir.
Yes.
I informed to sir. I think we need to wait 2 more minutes, sir.
Okay, ma'am.
Okay.
Yes, ma'am. Slide is visible now.
Sir, slide is visible.
Yes,
Please
ma'am.
start the.
Yes, ma'am.
I can continue.
Yes,
Yes,
sir.
sir. You are audible, sir.
Yes, sir. Yes, sir.
Is it audible?
Please. Yes, sir.
Audible?
Please.
Audible?
Yes, sir. Yes, sir. Audible,
Okay,
sir.
Yes,
okay, fine,
sir.
fine, fine.
Or
Yeah, yeah,
audible as well as
yeah.
even
Okay, okay,
that slides are also visible, sir.
okay, okay.
Please.
Okay, fine, fine. Well. So yeah, let me start over here. So when you have the general carbon cycle matrix optimization, there would be what we call the content vector. The content vector is dc by dt, which is ac plus ct. And when you write this in terms of matrices, you get what we call atmospheric the matrix, and O is response for the ocean, and V is the vegetative matrix. Well, we have seen the climate downloading scales. When you talk about this abrupt variations, we model by using what you call a prognosis approach. Prognosis approach is nothing but we talk about the local variables at discrete points. We'll try to trigger into a global matrix. That means we make into small local values. These local values we will make a topology connecting each other and try to assemble it. Okay, that is what is called the statistical downscaling. There is another method what we will call quantile mapping. That is also very, very important. But only thing is the mapping should be cumulative, should be invertible. Then only we can use the quantile mapping. Other one is what we call a Monte Carlo climate simulations. That is, whenever you have this uncertainty, this uncertainty can be avoided by using parameter uncertainty. That is, theta is approximately equivalent to the p of theta, where run variables are m theta 1, m theta 2, m theta, etc. And these will become what we call a sensitivity estimations, which we call it as a Bayes estimation. And the likelihood function we construct it based on this likelihood function, we'll try to trigger the best approximations. And there are other ways of doing it, that is called climate impact assessment methods. That is what we call it as dt is nothing but b1t plus b2t. That means a linear approximations by using what we call a damage coefficients beta 1 and beta 2. And ultimately we compute what we call social cost of the functions with respect to the discount rate. And when you talk about this battery mathematical models, the terminals, we use it in terms of the columbial efficiency by using the different wavelengths and different frequencies. And we wanted to optimize this subjective function subjected to the different storages. Storage at one point, storage at secondary point, storage at the discrete points. So those will become what we call a nonlinear optimization problems. Then we call it as the power flow approximations. So therefore, whenever there is a distortion, whenever there is a translation, there would be a factor which does come up because of the distortion or translation. That is what is called a Jacobian, which we do it in the calculus also. So when you keep on iterating, we need to have a scalar variable at the end, which we call it as a Jacobian. And because of this iterative procedure, we use a Gauss-Seidel iteration procedure in order to get the best approximations. There would be a grid stability analysis using eigenvalues, and sigma I becomes a 0 stable, and if it is greater than 0, it becomes unstable in order to handle the oscillations over the different frequencies. Well, there will be a what we call the what we call renewable energy integration challenges, and how actually the frequency will be regulated from one phase to the other phase. There will be a planning and a net planning, economic optimization, and portfolio optimization. All of you might be knowing very well. Portfolio optimization is very, very important, especially in the energy conservation, and there will be black holes. Therefore, higher the temperatures, how you could able to minimize in order to make into the cloud bursting one of the important example which we see in atmospheric dynamics. And recently we have computed a what we call pin based, that is physics informed neural network for load forecasting, and we could able to devise a new architecture for the smart farming, and in fact we have got one patent also based on those things. So therefore, in my last 1 hour and the 20 minutes talk, although there were one or two disturbances, I could able to give you the quantum computing for optimization examples, digital twins for energy systems, and Internet of Things. And we need to handle at multi-scales. Multi-scale analysis is very, very important thing, how you could able to get into those analysis. So therefore, there is energy systems will give you what you call a climate models. Climate models will give you economic models, and they will give you policy analysis and for the economic efficiency of the sustainability of the neural networks and deep learning analysis. So therefore, the idea was how actually you could able to give a more important insight into the analysis and of different approaches. And in this, we use what you call linear algebra, numerical methods, the Internet of Things, and the CFD analysis and machine learning approach. And above all, there is a what you call principal component analysis, which is very, very important for making the multi-objective optimization. So thanks for all of you for getting connected me with this a small piece of work. And in fact, it is a very versatile. I have got some literature, and I can send the PDF files if those people who are interested in my talk. So thank you once again. And for the next few minutes, we would like to have some discussion from the participants.
Thank you, sir. Any questions from audience? You can ask. Any questions?
Yeah, please.
Please. We will share you the feedback form within 5 minutes. If you have any questions, please, you can ask.
Yeah, I think she has got a good
Okay,
number
sir.
of participants.
Shall
I see a lot of
okay, sir.
participants.
Okay, sir. Shall I conclude, sir?
Yeah, please.
On the behalf of everyone here, I extend our heartfelt thanks to Professor Sreenivasa Chary for sharing his time, insights, and expertise with us today. Your talk has not only deep-ended our understanding of climate change, but also inspired us to think more critically and creatively in our own academic pursuits. We truly appreciate the clarity, depth, and passion you brought to the session. It's been a privilege to learn from you, and we hope to continue engaging with your work in the future. Thank you once again, sir, for making this seminar so enriching. Thank you, sir.
Okay, thanks
And
you
thank you
once
all
again.
for being such an enthusiastic audience. Thank you very much, audience. We have just explored some fascinating insights, and there is one more to come. To guide us through the next segment of today's program, I am delighted to invite my colleague Navyashree, Assistant Professor, Department of Mathematics, to take over. Thank you very much. We will share the feedback within 5 minutes. Navya, please take over.
Thank you, ma'am. Good evening, everyone. A very warm and pleasant evening to the distinguished speakers of today, Dr. Sreenivasa Rao Garu and Dr. Sreenivasa Chary Garu, and also my faculty and fellow participants for this FDP program.
Navya.
Yes, ma'am.
Navya. I will wait for the next speaker. Sir didn't upload his PPT, na?
Okay.
Navya,
Okay,
just
ma'am.
wait for a few minutes. Sir will join. After that,
Vidya, please upload the SARS PPT, ma. Vidya, ma'am, please upload SARS PPT.
Ma'am, she's uploading. Just a second.
Okay. ఇంకా నాలుగు చేద్దాము.
Can you all see the presentation?
Yes, ma'am.
Is sir here? Srinivas sir, are you there, sir?
Yes, ma'am. I'm seeing the presentation.
Yeah. So,
I
yeah. So when shall we
Navya
start?
can start.
Navya, you can start, I think.
Yeah, ma'am. Thank you, ma'am. Once again, good evening to everyone. Good evening, sir. I, Navya Sri, Assistant Professor at Department of Mathematics, take this privilege in introducing Dr. S. Sreenivasa Chary garu, Scientist H and Technology Director for High Performance Computing, DRDL Hyderabad. Sir has completed PhD from Usmania University, Hyderabad. Sir also holds advanced diplomas from Carnegie Mellon University and George Washington University from USA. With over 34 years of service in DRDO, Sir has made outstanding contributions in secure operating systems, trusted computing, and high performing computing. Apart from his professional excellence, Sir's research interests include technology, geopolitics, and sustainability. We are truly honored to welcome you, sir, today and looking forward for the inspiring and knowledgeable insights and expertise from you. Stanley College for Women welcomes you, sir.
Yeah.
Over to the session.
Thank you very much, madam, for kind words of introduction.
Thank you, sir.
I hope I have control back on this thing. I should be able to move my slides. Okay. Good evening, all the participants and the respected staff who are conducting this interesting course. So my experience has been basically on the practical side of the issues. Hence, I will be just highlighting the important points regarding the topic allocated to me.
Sir, sorry for disturbance. Sir, I just made you as co-host. I think now you can access the slides
Pardon?
which I shared. I made you the co-host, sir. I think you can access the slides which I shared just now.
Without?
Because I shared your presentation, no, sir. I think now you can access that.
Right. Now, what I'm just thinking is do you have control to move it to the next slide and all?
Yeah.
Yeah.
Just a minute, sir. Vidya, what you done
Right,
for
right.
Ramanamurthy, sir, do the same.
Okay, ma'am. Sir, you can continue, sir.
Yeah. Yeah, ladies and gentlemen, this course has been into second day, and you already gone through three major lectures on the topic. I'm sure you already appreciate the issues involved in the sustainability and the issues related to environment as well as climate change that is taking place over the period of time. Okay. Now the point is simple. Can we save the only planet which sustains life in the entire universe? The fact of it is that we have only one planet which has life so far to our knowledge and is sustaining us for billions of years now. And due to our own activities, the very question, very survival of the planet is right now in danger, and all the issues related to that are being told out. Now, can I move to the next slide, please? I don't seem to have control here. Okay. Now, the challenge is simple. The climate disaster that we are seeing is anthropogenic. Anthropogenic basically means it is something which is coming out of our own activities that have been taking place for years now. We are responsible for pushing planet Earth onto ventilator. Okay. And the results of it, in fact, for the last 1 decade, we are already seeing it. The climate change is no more some remote possibility, or climate change is something which is only something in the realm of scientific and technological thinking. Now, common man is able to feel the implications of that. Many places in the world have registering temperatures beyond 50 and untimely rains, unexpected floods. The kind of rate at which the snow is basically melting at the heights of Himalayas as well as Arctic base. We are all seeing the implications of that, and we know what is called climate change and what is the implication for us. Please go back to the previous slide. So this is all the result of our own activities. It is a result of human activities. So it is the responsibility of human beings to set it right. Though it is not yet curtain set, there's a serious problem. We do not have much time. So consequently, it is imperative that the world leadership takes a serious policy stance on this and tries to put in measures which basically try to meet the what were projected as Paris Agreement requirements of achieving 2 degrees less than pre-industrial levels for temperatures, average temperatures all across the world. And this is the most important challenge for us. Next slide, please. Next slide, please. Now, the point is we all know the reasons for this climate disaster. What has been happening for the last 3 centuries? See, human race has seen waves of progress. First was what we call agricultural revolution, which sustained the human presence on this planet and actually helped the human population to grow here. Okay, so agricultural revolution was a progressive step which helped human race to further itself on the planet. The second major revolution which has come is called industrial revolution. Industrial revolution started with the mechanical tools, appliances, which help us to speed up the production. Initially, it was driven by, again, a human effort. But once we moved into the kind of technologies which allowed us to make use of boiled water, which allows us to make use of biofuels, which allows us to make use of electricity to further the production, to further the rate of realization of the things. The seeds of what's called climate disaster were sown. So fundamentally, what happened is as long as the effort for development is based on human effort, it was proportionate to the what environment can really handle and what is the healthy rate for growth for all kinds of life forms in this planet. Now, once we have invented the machines which can actually generate things at a pace which is much faster than our environment can hold, we started having problem with the climate. So essentially, the industrial revolution that started in 17th century and already passed in more than 250 years has created the kind of industrial infrastructure and the kind of human facilities which are all based on energy consumption. And this energy consumption hunger, both from the infrastructure point of view and also from production agency point of view and from consumption agency's point of view, is simply going year by year. Added to that, the stress of growing population. Obviously, there is more need for this energy and more consumption. That is the first part of the problem. Second is to meet the requirements of huge population that we have near to 800 to in near future maybe 1,000 crores of population. We have increased agricultural production, food production, which is essentially centered around a chemicalized approach in terms of increasing the output of the agriculture. We have fertilizers, we have chemicals, we have other means of food production, which speed up the and quantity of food production has increased, but consequently resulted in impact on the environment in which this activity is being carried out. The other part is over-exploitation of natural resources to meet first and second targets. We wanted oil, we wanted natural gas, we wanted coal, we wanted many other minerals. They are all part of our environment. They are all natural resources, and we have been exploiting these natural resources at a growing rate for a long period of time. Added to this industrial revolution impact, we also have from last 60-70 years what is called the communication and computational revolution, which has brought in its own needs for energy. And today and probably tomorrow in future, the computational requirements are probably going to be most important driving factor for energy generation and consequently energy consumption and the impact on the environment. Now the point is, we know that these activities are causing impact on the climate, but can we really avoid them? We have large population today to support both from point of view of food sustenance as well as the comforts that are needed to survive on the planet. Now, the way currently the levels of wealth is organized, northern portion of the globe has is already well developed, has control over the both economic resources as well as natural resources. But southern portion of it is just developing. There is absolute need for them to reach a basic minimum sustenance level. So while the issue of northern portion of the world is how to basically continue to grow without impacting the environment, for southern people, how to reach sustenance levels without impacting the environment further. The problem is very complex. It has social aspects to it. It has economic aspects. It has political and technological implications. The now challenge before us is, can we find solutions which are sustainable and equitable? We need technological solutions which result in repairing the planet, repairing the environment around us, and have a model of sustainable development. And also, those solutions should be equitable. If the solutions, technical solutions which we are proposing developing are going to help only people who are already developed and have financial resources to own it, then that is not equitable development. So whatever solution that we find for climate change challenge has to be both technologically sustainable and equitable to the people. This is the most important challenge for us today. Next slide, please. What is the solutions, please? We all know basically the reason for climate change impact that we are seeing is excessive usage of fossil fuels and resultant carbon dioxide release into the atmosphere and consequent greenhouse effects. And we are seeing the increase in temperatures and the impact of it over our oceans, over our land, over our agriculture practices, or health of the people. Now, can we stop using the fossil fuels? Let me tell you something. This whole effort at trying to contain the climate change seriously started in 1990 with United Nations framework for a sustainable planet. And since then, we are already 35 years past. Today, at this point of time, even today, our energy mix is still about 85% from fossil fuels. The reasons are simple. The reasons are there are no alternatives which are satisfying the reasons of availability, the economic considerations involved, and the technology to harness the energy. They are still available with fossil fuels only. So as on today, our energy mix still is 85% fossil fuels. Only 15% is, we may call it sustainable energy or renewable energy or whatever we may call it. So that is only 15%. Ultimately, if you want to really control the release of carbon dioxide into the atmosphere, which is our main goal, we are a long way to go. Even by 2035, the target is when we probably want to meet 2%, 2 degrees centigrade lesser than pre-industrial level. There also will be just around 75% fossil fuel. Okay, so that stop using fossil fuels is not an option as on today for various reasons. The other option solution space is find sustainable alternative fuels. There has been a lot of effort to moving towards alternatives to fossil fuels, and a lot of technology developed, a lot of funds are invested in solar energy, in electrical appliances and electrical transportation processes. Then, of course, research is going on in hydrogen, sustainable hydrogen sources as the energy, both for transportation and running the industries. And of course, age-old hydroelectric solution is always there. So finding sustainable alternative fuels has been, energy resources have been happening for the last 30 years. We are making some progress, but most of them have not reached the level where they can completely replace the fossil fuels. Other aspect is to achieve sustainable level. What we are using today, can we control the usage of energy at the current levels or reduce the rate of growth of energy consumption? For the last 50 years, every year on year, we are seeing 2% increase in the consumption of the energy. If this process continues, there is no solution for the climate change problem. First is whether we can stop at this point, or at least from 2% can be reduced to 1%, 0.5%, and slowly reach a point where we peak the energy utilization and stop further increase in energy utilization and do more with less energy. When energy is constant, population is growing, requirements of the industrialization, communication, computation is growing. How do we achieve all these targets with a cap on the energy utilization? That essentially leads to do more with less energy. We have solutions which help you to deliver more services, deliver more results, more goods, more products with a limited energy. Do more with less energy. That is what we call energy efficiency. This is the key component in realizing or move towards climate change containment and sustainable development model. Next slide, please. So if you look at environmental sustainability, there are a lot of things we need to do, as we have discussed. There is a need for ecological restoration. So essentially, what is the problem with climate change? We have more CO2 in the atmosphere trap, which is causing the temperature increasing in the environment. If you have a model by which, if you release CO2, carbon dioxide to the atmosphere, we have ways of taking that back into our system from the atmosphere, then we will reach some kind of balance. Okay, that will happen only if you have carbon dioxide sinks on the planet. So typically, what we have is a forest. Most deforestation resulted in loss of such things. Now, to restore ecological balance, people are trying to do afforestation again and sustain the existing forests. So this ecological restoration in forests, water bodies, and the sea, the poles, all these things, ecological restoration process, one angle in which people are working on that. Then biodiversity preservation. There is another group of activities which are being done for environmental sustainability. It is not a question of climate change alone. Basically, preserving the biosphere that we have inherited and passing it on to the next generation is the biodiversity preservation, and it has a side impact of sustainable environment. Then reduction in fossil fuel consumption. Then you have looking for renewable energy. Then energy efficiency and conservation. Then corresponding behavioral changes in the way we are doing the things. Then, of course, in international cooperation. Recently, we had some kind of setback where major countries have actually gone back on their commitment towards Paris Agreement and Kyoto Protocols. Hope things will change in future. Now, coming to the today's topic, the energy efficiency. What is the energy efficiency? In simple terms, energy efficiency means using less energy to perform the same task or produce the same result. Today, we are using X amount of energy to get a Y output. Okay. Tomorrow, can we get same Y output with X minus P amount of energy spending in the process? So basically, with less energy, get the same result. Other way of looking at it is energy efficiency means using the same energy to perform the same task in lesser time or produce the better result. You use the same result, same energy, but try to complete the task. And if it is a task which consumes time and lesser time, if the task is production of more things, get more things or better result. That's another way of looking at it. Other is energy efficiency also means using lesser rate of increase in energy. When you scale up a problem, scale up an operation, the energy required should not be growing at the same rate as the rate at which the result is coming. So rate of improvement should be much higher than rate of energy requirement when you scaling up. These three essentially form the framework of energy efficiency, getting an efficient result in terms of lesser energy or better results with the same energy, or when you scale up a process, scale up production or scale up operations, scale up services, the cost of energy associated with it should not grow at the same rate as the rate at which the operation is growing. Okay, For example, this slide itself is not energy efficient because we have 3 times told energy efficiency means this. And every time I tap something, it actually consumes some energy. So every process, there is a scope for efficiency. Next slide, please. Now, if you look at energy efficiency, there are several aspects. Okay. First is economic considerations. You buy a car. You look for a car which gives you more kilometers per liter. Okay. That is going to save you money. Okay. That is one aspect of energy efficiency. Typically, efficiency, when we talk about in terms of individual perspective or a corporate perspective, we look at economic benefits that accrue out of energy efficiency. The other is the public health from community point of view. When you the results of whatever operations we do with the energy are going to have a side impact on the whole system you're working. If you reduce the energy consumption, public health has a positive impact on that. The other point is every country has limited resources. Every community has limited resources. A country like India, which almost imports 80% of its crude oil, almost 70% of its natural gas. So energy security can be achieved only if you are able to utilize energy more efficiently, do more things with the lesser amount of energy that we are importing. So these are all aspects of energy efficiency. If somebody is looking for efficiency energy, it could be out of economic considerations or public health issues, or basically to have energy security. Because sources of energy are limited, they are expensive. You have to actually use hot and foreign exchange to get that, and they are also dependent on geopolitical considerations. So these are all the aspects, but our focus here is more on sustainable energy from climate change point of view. So mitigating environmental consequences, whatever energy efficiency we are talking is in terms of mitigating environmental consequences. In the process, they may result in above mentioned benefits also. In most of the cases, efficiency results in economic benefits, also energy security. But in some cases, it may not be true, but still have a good impact from climate change point of view. So our consideration of energy efficiency is about mitigating the environmental consequences. Next slide, please. So if you look at environment, how important factor is this energy efficiency? The energy production and consumption significantly impact the environment, both activities. Okay, industrialized production of energy. Okay, and I'm not talking about the produced energy consumed by us, but the process of production itself has a lot of impact. And for example, coal-based electricity production has huge impact on the environment surrounding it. Okay, produced energy consumed by vehicles, they themselves also have impact on environment. So energy is something which creates impact both at production stage, at consumption stage, and in some cases in transportation stage also. Okay, so now fossil fuel based energy sources such as coal, oil, and natural gas release greenhouse gases when burned for electricity, heating, or transportation. This is what we mean by impact on the environment. And these emissions contribute to climate change, air pollution, and disruption in ecosystems. Now, the energy is directly related to the disruptions that are happening in ecosystems. Okay, next. Now, seen from this point of view, energy efficiency stands as foundation in the pursuit of sustainable and environmentally conscious energy practices. We have already seen it is not possible to altogether give up on biofuels as we stand today. On fuels which are having greenhouse effect, we are not in a position to throw them away. So it is how less use and get how much work done. That what we call energy efficiency is the foundation that is going to provide a sustainable solution for us. Therefore, enhancing energy efficiency becomes instrumental in mitigating these environmental consequences. Energy efficiency plays a pivotal role in reducing the environmental footprint of energy production and consumption. Yeah. This is why energy efficiency is extremely important. Most of the talk always happens in terms of, okay, I found an alternative fuel. There is so much of excitement about using electric car or using the renewable resources like solar power or tidal power, whatever you get. Okay, it's always focuses on the sources of energy, but sources of energy are not going to help us immediately in short term. Maybe 100 years down the line, we may find renewable energy sources which are going to actually help us in fully meeting our requirements without getting into greenhouse effect. But as on today, it is not the sources we have to focus on. It is on efficiency with which we use those sources to get our output done. So energy efficiency is the most important foundational parameter for sustaining the planet and avoiding the climate change. So improving energy efficiency across industries, buildings, transportation, appliances reduces the amount of energy needed from fossil fuel-based sources. So these are the basic areas which we have identified over the past few decades. Where is our energy going? Most of it, and what is causing the most impact on environment? First is our own dwellings. In northern hemisphere of the globe, it is the cold atmosphere. Heating houses is the most important task for sustenance there. In southern hemisphere, in hot atmosphere, keeping it cool is what is most important parameter for a good residence, a good house building, or to carry out a good work in official building. So these building designs now are constructed in such a fashion that we utilize plenty of energy for various purposes, from lighting to heating or cooling to actual movement, like lifts, like escalators that you have in the buildings, and for circulation of air. For many ways, we are using energy for that purpose. So buildings are one of the most important and major consumer of energy. It's not just residential building, but commercial complexes, industrial structures. Okay, whatever you take, buildings by their design have never been very energy efficient. They are mostly focused on giving you comfort and the best experience. Now the focus is slowly shifting towards achieving energy efficiency, and a lot of policies and guidelines which are coming into place, and particularly in public structures, to ensure that building should use its location and the natural environment to get a good air circulation, either for cooling purpose or for heating purpose. Good lighting without actually augmenting with artificial lighting that requires energy. So the buildings are one area of concern where energy efficiency people have been working. Then the second is transportation, movement, personal vehicles to goods transport. There is a complete spectrum of transportation needs in today's world. So individuals moving is one aspect with various levels of efficiency, starting with a two-wheeler to four-wheelers to luxury car brands. Then you have public transport, you have buses, you have trains, then you have large-scale goods transport like ships and air transport. All of them consume huge amount of energy, and the cost of final output also adds to this cost of transportation that takes place. And for last couple of decades, there is a lot of focus on transportation. How to improve their operational efficiency means to get probably more kilometers per liter, as well as how to reduce the contamination in the greenhouse gases that are being released as part of the process, and how to actually organize them in such a fashion that there is no redundancy and you get an optimal delivery of any item from source to the actual consumption area. That could be movement through various ways of transportation. So transportation is one area where people are concentrating into achieving energy efficiency. And the other is appliances. It could be just household appliances or industrial scale systems which use energy. How do you make them more efficient? Okay, and work with lesser energy to deliver whatever work they are supposed to deliver. So these are the areas in which people have been concentrating. But apart from these things, of course, main consumption is in industries. How do you make industries what we call green industries? Okay, Industry 4.0 standard focuses a lot more on energy efficiency rather than on production efficiency. So these four areas are major points of study for energy efficiency. Okay, particularly because they are consuming most of the fossil fuel-based sources. This in turn leads to decreased carbon emissions, aiding the mitigating climate change automatically. Implementing energy efficient technologies and practices helps meet emission reduction targets outlined in the international agreements like Paris Agreement and contributing to global efforts to limit global warming. So essentially the focus of people who are looking for meeting the energy reduction targets like Paris Agreement or Kyoto Protocol or whatever we are talking about has been on energy efficient technologies more rather than on the alternate fuels. Next. Energy efficiency initiatives also contribute to conserving natural resources. This is again a natural process. All the resources we have on this planet are limited. So the sustainability goal is how to meet the requirements of current generation equitably and also how to pass on the resources to next generation. That is a sustainable development model. So if you consume all the natural resources which we have inherited on this planet and the next generation is left with nothing, then we excuse me. Okay, we get into issues. So energy efficiency is not just a climate issue, it is also an issue of conserving natural resources to achieve a sustainable development planet model and sustainable planet for the next generations. Okay, energy efficiency plays a pivotal role in reducing the environmental footprint of energy production and consumption, as we have noted. Next slide, please. Next slide, please. Now, this point is being recognized by the experts and international community. Okay, the importance of energy efficiency in terms of environmental protection. A strong early focus on energy efficiency is essential for delivering a net zero energy system by 2050. This is what Energy Efficiency Policy Toolkit 2022 of International Energy Agency says that. It recognizes that a strong early focus on energy efficiency is essential for delivering a net zero energy system by 2050. What is this net zero energy system? Net zero energy system is the name for a point at which the amount of greenhouse gases we are releasing to the environment are also taken back by a process, equal amount, to ensure that there is no further increase in the greenhouse gases in the atmosphere. So what you give out should be consumed in another process to generate the energy for the system. That is called a net zero. Okay, so net CO2 in the atmosphere remains same. This is another way of saying achieving the balance in the environment. Similarly, IPCC mitigation report in April 22 considered energy efficiency as part of major transitions in the energy. Okay. Then, most importantly, the first fuel of sustainable global energy system is energy efficiency. We have been saying that on one hand, people are looking for alternative fuels to the fossil fuels. On the other hand, energy efficiency to improve the utilization of the fossil fuels. What IEA says that this energy efficiency itself is the first fuel for a suitable global energy system before we get alternatives which are usable. So this is the importance of energy efficiency in overall achieving the overall targets of sustained planet and containing the climate change. Now, if you look at the whole process that is visualized from 2020 to 2050 and what has been happening from 2000 to 2050, initially this blue bar essentially shows it's the completely fossil fuel based energy, and by 2030 we're expected to reach a combination where there is some green fuels and there is some energy efficiency, which is blue lines, and fossil fuel continues to dominate. One important thing is from 2000 to 2030, there is a net increase in the release of the CO2 or utilization of the energy. Now, by next stage of 2040, the amount of fossil fuels come down. We have a green alternatives taking that place, and also energy efficiency going up. And consequently, the utilization of the energy has come down slightly. Okay. Then by 2050, when we hope to achieve net zero, it is going to be a combination of energy, green fuels or alternate fuels plus energy efficiency. This is going to probably put a cap on the energy utilization of the world, so that further on it will, without increasing the energy utilization, we will continue to have benefits of the development. So this is the efficiency which is going to be very, very important in process of doing this. Next. Reducing the amount of energy required to provide products and services, we call it energy efficiency. There is an interesting term called a megawatt. Is a watt of energy that you have not used through energy conservation or the use of energy efficient products. Okay, this terminology, like megawatts, are for the amount of energy that you consume as part of your process, whether production or service line. A megawatt is amount of energy that you have saved, that you have not used. So the efficiency of your system is going to be measured in terms of megawatts, while your production is going to be in terms of consumption of megawatts. Next. So if you look at energy efficiency, what do you mean by energy efficiency? Is it a single solution which will solve the problems of industries, transportation, various other use cases we talked about, like buildings, then the computational requirements, whatever you call it. Do we have a solution called energy efficiency which solves, or do we have technology which solves all of it? It's not the case. Energy efficiency is not a single technology, but a characteristic of every technology and process. Whatever we do, energy efficiency should be the basis for the model, the plan, or the execution that we do it. So it is basically a characteristic of every technology and process. So whenever you build something, you should look for efficient solutions. Now, when that is true for household appliances, industrial and commercial process, built environment, transport, digital technologies. Now we know about this star-based energy rating, which will tell you from product to product what is the energy consumption rates. So obviously, all these products involve technologies which are either improving the efficiency or reducing the consumption of energy as part of the appliances. So when we talk about energy efficiency, we are talking about a set of technologies which are relevant to that product or that process. Now, if you want to achieve energy efficiency, it is important that there should be a tangible way of measuring it. How do you say a product or a system is more efficient, more energy efficient? So there should be some way of defining it and keep track of that particular parameter to ensure that we are achieving the efficiency as we claim to have. But then, as we told, just as the technologies are different for different products, energy efficiency measures are also going to be different for different products, processes, and systems. But at the most general level, we may define energy efficiency, epsilon, as the ratio of useful outputs to physical energy inputs. So epsilon is equal to Q by E. So what is Q, what is E, basically depends on the process you're handling as part of a particular system or an appliance or a part of an operation. So there is certain amount of energy inputs and there is some output which is coming out of that. Okay, if you take a automobile, a car, the energy that you are giving is the petrol or diesel in so many liters, and the output is number of kilometers travels. So energy efficiency is, we can say simple KPL, kilometers per liter, is an energy efficiency measure. Okay, higher KPL, it is more efficient. That is how we are going to look at it in terms of vehicles. Okay, then there is an equivalent or alternative terminology called energy intensity. This is the inverse of this energy efficiency measure. I is E by Q instead of Q by T. and it maintains the competitiveness of a product or a system or a country in terms of energy efficiency. Basically, whenever we are talking about the countries or the organization, we talk in terms of energy intensity. And when we talk about the appliances or technical solutions, we talk in terms of energy efficiency. So these are interchangeable terms, energy efficiency and energy intensity. The relevant system may vary in the outputs it provides. Some may give light as output, some may give heat as output, work as output, wealth as output, and its scale. It could be a small light bulb, it could be a machine tool, a firm, a sector, a national economy. So what we call Q will change from application to application, system to system, and process to process. Next. So depending on the system and purpose at hand, it may be appropriate use what kind of Q and what kind of we use. It depends on the kind of system we have. Some of the examples given is thermodynamic measures like enthalpy and exergy that used in mechanical systems. Okay. Then physical measures like vehicle kilometers or tons of steel, tons of oil, or economic measures, gross output. Okay. So dollars per liter of crude oil, we can say that. Okay. Then gross domestic product generated by using this much energy, or expenditure on fuel of inputs and outputs. So how much money you spent in acquiring the fuel, and what is the output of money that is generated. Okay. So energy efficiency measures also differ in how they aggregate qualitatively different energy inputs, like how like summing up of kilowatt hours in a productive process, such as factory, or weighing up relative price. So there should be a formula of combining it. What is the cost of energy inputs that is going to into the system, and what is the value of the output that is generated? It varies. It is very clear that it varies from application to application, system to system. But broadly, it is the amount of energy which is going in, and it is the amount of value which is outputted out of that system. Next. Next, please. So once we start looking for target energy efficiency, what are the targets, target areas that we should be looking for? So obviously, first thing is the moving towards non-greenhouse energy sources. Does it come under energy efficiency? It does in some sense, that because energy input also has a cost. There is a cost difference between hydropower and fossil fuel, or hydropower, wind power, or solar power, or whatever. So moving towards non-GH, non-greenhouse energy sources also has the cost benefit. Hence, that is also an energy efficiency mechanism. So the alternatives to have a renewable resource like solar, wind, hydropower. Okay. Though all of them have their own limitations. You can have a solar power only when sun is available, and solar power when in the countries which are very having strong summers. Wind is also possible only when you have atmospheric winds going on, and in the areas where it is windy only you can have it. The hydropower requires water to continuously flow. In some rivers it is possible, some rivers it is not possible. But when the energy is generated, it is considerably cheaper in terms of cost, in terms of resource exploitation, and also they are all renewable. It is not something which gets over. So moving towards non-GH energy resources like renewable resources contributes to energy efficiency. Then carbon neutral fuels like synthetic fuels and biofuels. Synthetic fuels are generated using atmospheric carbon dioxide. In that process, you are actually taking CO2 from the atmosphere and creating synthetic fuels. And there are some biofuels which have a cycle which is also CO2 neutral. Then hydrogen. Now, one of the exciting field of fuel development. Hydrogen problem is we can either say it is environmentally friendly, environmentally unfriendly. It all depends on the production mechanism that you use for hydrogen. If you make hydrogen using the environmentally friendly methods or without impacting the environment, then hydrogen is most likely a sustainable energy solution and also contributes to the energy efficiency. Then going back to the actual consumers of energy, industrial units now have a very strong process associated with energy management, starting from conceptualization from design stage itself to the production end, and with continuous audits to ensure that energy efficiency is there at every stage of operation. It is not something which gets over in one part of the operation. And we see a lot of models which are proposed, which are implemented, and green industries are there placed in various segments and sectors of the activity we have seen that. Then buildings that green building norms are in place, and most of the large building structures for public purpose as well as private purpose are basically by policy are made to be compliant with requirements of environmental friendliness. Then transportation. In case of transportation, working out an efficient mix of road, rail, water, and sky transport is one of the major areas of planning and work today. If you deliver a product from production to the consumption, it may go through all these things. And what is the right mix so that overall energy cost of transportation of the product is minimized? There are a lot of models which are proposed and also implemented in many countries. Then when transportation at a level of the vehicle, the capable improvement with better technologies is taking place. Year over year, we see several kilometers improvement in the automobile outputs. Then we are also moving towards electrical vehicles, which are not non-greenhouse releasing systems. But when it comes to electrical vehicles, the overall cost of the energy that we take into consideration from the point of view of impact on the environment is not just the vehicle efficiency alone. Now, vehicle is not releasing any greenhouse gases. Doesn't mean that it has no impact on the environment. To manufacture these electrical vehicles, particularly the batteries which hold the power for them, there are various industrial methods are followed. All of them have impact on the environment. So solutions which are environment friendly is what is the area of research today, and a lot of progress is made in that direction. The other aspect is that electrical vehicles also utilize power, electricity, and that electricity is generated somewhere using mostly by fossil fuel, because current mix contains maximum fossil fuels. So the electrical vehicles, while make progress towards environment-friendly solutions and also what we call energy efficient solutions, it doesn't mean that they are some kind of net zero solutions. Then again, a lot of research is going on hydrogen fueled vehicles and looking for solutions which contribute to the generation of hydrogen without impacting the environment. The most important and very interesting consumer sink of current electricity is data centers. People don't realize that. Actually, the industrial units, buildings, transportation, and all these are all conventional consumers of electricity. But data centers, as I told, last 50 years, we have had a revolution in communication and the computation. Now data is the new gold and new oil. That's what they call it. So data is the most important thing in individual's life, in corporate life, and in nation's life. So to store this data, we have large data centers built all over the world for various purposes. One is storage of the data itself. Second is the computational requirements. Third is to provide services. Fourth is to achieve scientific breakthroughs. Okay. So the data centers of various use we have. We have data centers which provide various services like storage as service or software as service or computation as service, whatever. So they are actually their size unnoticeably grow to a level where today they are almost occupying about 1% of the total electricity consumption all over the world. Okay, and with the latest developments in artificial intelligence, which requires large amount of computational power and consequently large data centers to achieve them, the consumption of electricity by data centers is the biggest challenge that we have today. By 2030, it is supposed to expected to double in terms of electrical consumption, and in real magnitude terms, it is likely to overtake the entire electricity consumption of a country called Japan, which is highly industrialized, by 2030. So one sector alone, one small area called data center is going to consume the amount of energy by 2030, which is more than the entire Japan is consuming today. Now, beyond 2030, it is anybody's guess. Actually, we are not even hazarding how much growth rate of these data centers is going to take place in future, mainly driven by artificial intelligence related applications. So this is going to be the new focus area, new target to look for energy efficiency. Next. So the general future trends in energy efficiency, apart from technological progress, technological solutions, we are looking at appliance level, at organization level, process level, and all. 2-3 things are actually supposed to be driving the future trends. One is the AI and automation, the smarter controls of any system, any process system is going to reduce the energy. We are typically talking in terms of control of lighting and heating. It is not this alone. Complex industrial processes are today controlled by AI and automation, and that logical progression is increasing. Contribution of AI to this is increasing day by day. In future, the factories are expected to achieve about 30% reduction in energy consumption purely by applying AI and its logic on it. Similarly, we have developed so many technologies over the period of time, and we have reached a point it is possible to have zero energy buildings, structures that produce as much energy as they consume. They are net zero. Okay. Similarly, next generation of batteries, because these batteries are what are going to contribute on one side to the electrical vehicles, on the other side to the data centers. So this next generation of efficient storage of power is what is going to determine the energy efficiency in future. Next. Next, please. So I want to take this case of data centers and study what is the energy efficiency impact on that. So as I mentioned, electricity demand for data centers more than doubles by 2030. That is the expectation of International Energy Association. Now, data centers accounted for around 1.5% of the world's electricity consumption in 2024, or 415 terawatt hours TWH is what is the consumption of electricity by data centers today, say 2024. Then the data center electricity consumption is set to more than double to around 945 TWH. In fact, on one extreme, there are people who are predicting it is likely to reach from 1.5% to 8% by 2030. So 8% of the total consumption of electricity is going to be done by the IT data centers. This is slightly more than Japan's electricity consumption today. AI is the most important driver of this growth, alongside growing demand for other digital services. Why AI is the important growth factor is because artificial intelligence has two portions in it. One is training the neural network, which is actually capturing the interest, and the other is, of course, doing the operation that you wanted to do, answering whatever intelligent operation you want to do. This training portion of AI requires large amount of computational power. Computational power is directly proportional to the consumption of energy. So they will need large amount of servers, accelerators to carry out training of this machine to make it realistically intelligent. So the number of servers which are going to be required is going to grow day by day based on the AI applications. Okay, so we have seen a 1 million server data center recently set up by Apple, and a larger data center is being planned by others. Now, these data centers are what? Data centers are basically concentration of computational power in a single space. It automatically generates heat. The amount of electricity that goes in proportionately increases the heat, and to cool that heating system, you need energy. So you need two different components of energy to run the servers in the data center to cool them. If you don't cool them beyond 40 degrees centigrade, none of your servers will. This is the 24/7 operation which keeps consuming the electricity. Now, the United States account for so far the world's largest. Obviously, they have largest data centers, and consequently, the maximum consumption in data center energy, followed by China. In the United States, data centers account for nearly half of electricity demand growth between now and 2030. Means all other industrial sectors are going to take backseat in terms of energy increase, and it is the data centers we are going to take 50% of the estimated energy increase. By the end of the decade, the country is set to consume more electricity for data centers than the production of aluminum, steel, cement, chemicals, and other energy-intensive goods combined. The point is, data centers are the going to be largest consumers of electricity in future. How well you achieve energy efficiency in data centers is what is going to determine how well you are going to moving towards a net zero kind of scenario, or less than 2 degrees target that we have. So data centers are the new strength. Data centers are the new danger. Okay, next. Next, please. Okay. Now, if you look at the environmental footprint of data centers, there are two things. One is the emissions originating directly. Yes, equipment with operations in data centers means when your servers, computational servers are running, they require power to run. Hence, that is the power consumption. Consequently, emissions will take place. It is something to do with data center operations. Okay. Then also cooling of the data center. Then there are emissions indirectly generated. Okay, the energy sources that you are using. If you are using greenhouse fuels, obviously emissions will be more. Okay, or if you are using renewable environment-friendly fuels, and consequently emissions could be less. Then there is a huge construction activity associated with data centers, which also consume energy and affect the environment. And there are several additional contributors like supply chains and many other things which take place. We are talking about literally billions of servers being manufactured, integrated, connected by the wires, okay, connected, pushed into various kinds of racks. There are a number of components, okay, which form a data center. All of them are generated at different places and transported to this place center. So if you look at the scale and the number of data centers that are going to come up, this indirect emission generated are also going to be very significant. When we come to data center efficiency, like we told that energy efficiency depends on the segment of the activity, or depends on the application you are running or process you are doing. When it comes to data center, there is a measure which is called power usage efficiency, which is most critical in terms of saving the energy and or optimizing the data centers from energy perspective. Okay, so we told that in a data center there are literally millions of servers which are going to be pushed into close proximity, and they're all integrated by various networking technologies that are taking place. Okay, so this much of power consumption in closed space is going to generate the heat, and that heat has to be controlled using some kind of cooling technology as a part of that. Now, what is happening? The power is consumed by the server generates you result. Okay, whether it is training in AI or whether you're doing computation, scientific computation or database operation, it does something which gives you a computational service. So that energy input is giving useful output. But there is other aspect which is actually going into the data center, is to cool this system which is generating heat. This is not giving any useful output to you other than making it operational. So total energy used is two components. One is the IT energy, other is non-IT energy. Okay, IT energy is something consumed by servers, switches, monitors, networking, blah blah blah. There are many components. Okay, actually, recently I have set up a large data center, probably country's largest scientific computation machine. I had an inventory of 489 different items which gone into that small to big. Okay, so all of them are power consuming items. Some of them are active, some of them are passive, but power is essential for them. Okay, then there is a non-IT energy part, cooling systems, UPS batteries, that is power support systems that take place. Now, the power which is consumed by this non-IT is not directly resulting in any benefit in terms of computational outcomes. Okay, so this is only something which is helping the operation to go on. Okay, so PUE in case of data centers, power usage efficiency is defined as total energy, which is summation of IT energy, non-IT energy divided by IT energy. Okay, is what constitute the PUE of the system. Okay, typically this is going to be above 1, and challenge is to bring it as close as possible to the system. Now, if you range between 1.2 to 1.5, it's considered to be a fairly efficient system. There are people who actually reduce it further down. Okay. Now, if you are looking at IT power consumption in terms of data center operation, is going to be the one of the largest consumers of your new power that is going to be utilized in the next 10 years. It is important that technologies are developed to ensure that PUE is pretty close to 1. Though mainly cooling systems contribute most to the non-IT energy consumption. Having a cooling technologies which form part of the data centers is going to be the biggest energy efficient area as far as data centers is considered. Okay. So now, if you look at Q by E that we talked about, the outputs and the energy which is going to it, it is very clear that non-IT portion is not generating any Q for Q. Okay. It is only contributing to the energy consumption portion. Hence, it is necessary that you focus on non-IT technologies to improve the energy efficiency. Next, please. Next. Now, strategies for sustainability of data centers. Now, if you are building a large data center, basically you have to focus on enhancement of structural design to consume lesser power. Plan emphasizing usual exposure to air, thermally advantageous resources, and optimal server outlines can lessen the requirement for synthetic cooling. Okay, so basically, if you set up a data center in a naturally cool area, your power consumption will be lesser. In the sense, like by the time the temperature goes up, the environmental factors itself is helping. A location matters. Okay, season matters. A cooling season, you don't have power consumption that high. So you create a building, a structure, or a framework for servers in such a way that you can exploit the natural conditions. Okay, so structural design is important. Then renewable energy sourcing. This is very important because ultimately the energy efficiency or environment friendliness of a data center is directly related to the kind of fuel from which the energy source is coming. Your electricity is mainly dominated by greenhouse gas generating fuels. Obviously, that is not what we want. Since 2014, for example, Apple company, which is one of the biggest producers of IT products as well as IT services, has used only renewable energy from sunlight, wind, and other renewable sources to power all its organizations worldwide. Together with data centers, means not just data centers, all its organizations worldwide, they move towards using renewable energy. So, what it means, if you want to use, for example, wind power, you have to put your operational center in a place wind power is feasible. You have to select the locations in the world which are suitable for meeting your target of renewable energy. It's not possible to have a wind power based organization, for example, in Hyderabad. We don't have conditions which are suitable for that. So your selection of location, taking advantage of natural conditions everywhere, is important if you are looking for renewable energy sourcing. And major companies are actually committing to that. For example, Amazon Web Services, which is one of the largest provider of data center services, has wind farms to counterbalance with the power usage of enormous system data centers. What they have done is that if they are consuming conventional sourced power in some countries, alternatively in other countries they are setting up more and more renewable energy source based power structures wherever it is feasible. So they're trying to balance the utilization of greenhouse gas fuels with environmentally friendly solutions to overall achieve a net zero kind of scenario for them. So it is important that energy sourcing has to be based on, if possible, on renewable energy source. Next. Then obviously, how do you improve the efficiency, hardware efficiency? Basically, data centers consist of servers. So server technology for the last several decades has been progressing in a pretty efficient way, with more and more transistors sitting on chips. In small area, more chip, more transistors, actually billions of transistors, more logic, more computational power, and less power consumption because of the technology used. Has been regular activity in terms of hardware design in the industry for quite some time. Not just the design, not just the manufacturing technology. It is also moving towards solutions which allow you to continue to do that. When silicon becomes saturated, they are looking for other things, gallium arsenide and many other things have come into picture to provide continuity of this growth. And not only that, basically whatever you do, whether from design to manufacture, it should be higher computational power per watt is the guiding principle. Similarly, they have moved towards from conventional hard drives, which consume a lot of energy, to solid-state devices with the equal efficiency in terms of accessing of data. Okay, so IT hardware industries is one of the dominating technological industries which have been working towards efficiency in terms of energy utilization for several decades now. Okay? And that is a continuous process, mainly driven by the competition within the industry. Okay. Then the other aspect is by reducing the requirements for many physical servers. So typically, then there are equivalent software developments like virtualization technologies, which are enabling multiple users, multiple applications to run on same hardware or quickly be migrated from one hardware to the other to ensure that need for one-to-one correspondence of physical servers are removed. If you have a server which is capable of running multiple applications, you create a virtual environment running. So hardware efficiency is both, server efficiency as well as software efficiency has been continuously growing. That is one area which is resulting in the energy efficiency per IT product of the consumption. Then the other is the, of course, as we told, cooling technologies, which is part of non-IT. Heat generated by the servers has to be reduced on a continuous basis. Then there are several cooling technologies. Typically, from olden days, we have been having air conditioning technologies, which have been used in small server rooms. Then cool water-based loops, which allow you larger systems to be functioning. Then there are technologies called inline cooling. Within the racks itself, between computational racks, you have the cooling sources placed in such a fashion that optimization of cooling can be improved. Okay. Then there are things like rear door heat exchange, where cool water loop goes through the rear door and the hot air goes through that, exchange of heat takes place, and it is carried to chillers to cool down again. Then you have more complex technologies like liquid cooling. There are some designs which ensure that from where the heat is generated in the system, at each chip level, at board level, wherever you have electricity going through, you have a source of heat. There itself, you cool it instead of making it come out. That's called liquid cooling. A liquid line runs along with the electrical line to ensure that whenever heat is generated, it is exchanged with this coolant liquid, which can take back the heat and at the source itself, reducing a large scale cooling required, external cooling requirement. That kind of complex technology with specialized coolants are also developed. Then recently we are seeing what is called immersion cooling technology. The entire server itself is immersed in a dielectric, which can which is a bad conductor of electricity but very good absorber of heat, so that the heat generated at the source itself is taken. This is also a developing technology which is going to contribute to the cooling, revolutionize the cooling scenario in the data centers. So there are a number of technologies which are coming up, number of solutions which are being found day-to-day basis, but that has to keep in pace with the rate of the new data centers that are coming up. Next. So if you look at the whole scenario, already major IT companies which are in the AI game have taken a lot of initiatives to realize this environment-friendly data centers. In 2015, the Project Natic team of Microsoft demonstrated the viability of underwater data center. Means entire data center boxed in is just thrown into water, into the sea. And what you have is only a connecting pipes which give power to it and take data out. Networking as well as power cable with a 105-day deployment in Pacific Ocean. Now, what is the advantage? Heat generated is simply taken over by the ocean water, which is a large source of coolness for the system. So this, from that point, now there are literally hundreds of data centers which are built into ocean directly, and only once in a year or two for the purpose of maintenance, you pull out the entire data center and do some preventive maintenance and push back. Now, what is happening? What we are supplying is providing it is only the power that is required for running the IT hardware, IT energy. Non-IT energy is now technically close to zero because all the heat generated in the system is taken by the seawater. The subterranean ocean's constant coolness also makes energy efficient data center business possible. They can, for instance, make use of heat exchange piping like that seen in submarines. Some of these technologies are already used in submarines which are underwater for several months. Similar technologies are being adopted in data centers to ensure that you don't require separate energy to cool down the system. The majority of people on Earth, now how is it possible? Why is it viable? Is that majority of Earth on Earth, people on Earth reside 120 miles or less from the shore. So data would have a short distance to travel if data centers were submerged close to coastal communities. This is proved to be both economically useful and environmentally friendly for many of the big IT corporations today. They have a lot of data centers operating underwater. Next. Similar cases are Google's zero carbon data center in Finland. Finland is pretty close to the North Pole and naturally very very cool area. In addition, it is very close to the sea. So Google's latest data center is located in Hamina, Finland, will only be chilled by seawater. What are they doing? Google plans to use the facilities existing tunnels to bring in cool seawater, mix it with cold water to make it roughly equal in temperature to the water it is returned to after passing it from site to site heat exchangers to scatter the temperature from the servers. So basically, it is taking advantage of the location of the data center to achieve energy efficiency for non-IT, which is the energy which is not giving you a useful output, reducing this. And there are many other technologies being used by the large players like Microsoft, Google, Amazon, Oracle, and also Apple towards reducing the cost of data centers, improving the energy efficiency, and particularly from the efficiency which is non-IT purpose. So the energy efficiency research and direction development in data centers is going to be critical from the point of view of achieving 2030 targets or 2050 targets, because that is going to be the main driving force for energy consumption that is going to come into the picture. Next. Next, please. Next slide. The other aspect is that we know AI is going to be the energy guzzler, it is already reached that point, and in future most of the energy is going to be used by AI. But on the positive side of it, now many analysts and experts feel that the capability of AI to achieve the optimization that is required is going to help in energy efficiency in future. AI could unlock major efficiency and operations gains for energy sector. AIs are already being deployed by energy companies to transform and optimize energy and mineral supply, electricity generation and transmission, and energy consumption with amazing results. People are talking about 30 to 40% benefit in terms of cost. Then the oil and gas industry has been early adopter of AI, using it to optimize exploration, production, maintenance, and safety. Last 2 years, a lot of new discoveries were done by AI, AI-enabled exploration agents. AI can help balance electricity networks that are growing more complex, decentralized, and digitalized. There's one more thing. AI has potential to decrease the transmission losses. Okay, that's one of the wastage of energy that is taking place in the grid in most of the countries. Now, to actually understand the complexity of the networks from main grid to the subgrid to subgrid that is taking place, and the balancing the and movement of power based on the based on utilization, it's very complex process. Now AI is coming in to help to ensure this balance in electricity network and reduce the energy losses. AI applications in transport can improve efficiency and save costs, but they could also increase demand for personal mobility. Both ways it works. In buildings, there is significant potential for AI-led optimizations to make heating and cooling systems more efficient and electricity use in buildings more flexible. In general, AI is expected to drive innovation in energy efficiency in near future. AI is actually bringing innovation in many segments, and in energy sector itself, large-scale innovations are expected because of utilization of AI, both from conception to planning to providing algorithms and efficient solutions. AI is going to be a driving factor in improving the energy efficiency, is what the experts feel. Next. Next. Now, this is all what has been happening all over the world and the issues involved in energy efficiency. Now, coming to India, like what is our view on this climate change mitigation or the required solutions like energy efficiency? India is not a significant contributor to climate change in the past, at present, or likely to be near future, as revealed by actual empirical data and modeling results on future carbon intensities. Past we can understand because India has not been so much industrialized. But present, we definitely is a much more industrialized country, much more digitalized country, and in future we are growing at the rate at which we expect actually the manufacturing, the services, the digital space to grow very rapidly. But despite that, our empirical data for the past and the modeling shows that we are not, our contributions to destruction of environment is insignificant. We have not really done that. This is something very interesting because the countries which have actually contributed to the climate change by destroying the environment are the people now expecting the others to bear the cost of protecting the environment. They do not want developing countries to use fossil fuels because that they're going to create greenhouse effect. But without using fossil fuels, industrialization development is not going to take place. So this is something, as I mentioned earlier, it has economic, socio, ethical, and geopolitical considerations. So as far as India is concerned, we can safely say that our contribution to negative impact on climate has been minimal. However, India is among the worst sufferers of climate change caused by industrialized countries. This is because of the nature of our geography and the location we are placed. For example, melting of glaciers in the Himalayas, unusual floods, unexpected sheets of rain, okay, and raising of sea levels, and complete disturbance of the environment and weather system that is happening in India. India is a unique weather system in the sense we do not see this concept called monsoons anywhere else in the world. And they are very, very delicately balanced based on the weather system all across the world. Okay, if something called El Nino takes place somewhere in the Pacific Ocean, we don't get rains here. Okay, and La Nina is going to bring more rains. This kind of dynamic interchange of world weather and very delicate balanced monsoon system that we have is highly disturbed by the greenhouse effects that are caused by the industrial activities by the developed countries. So while we have not contributed to the climate change much, we are the receiver of the impact of the climate change most. For that matter, South Asian countries, all of them. India has taken a number of policies. Keeping this in mind, India has taken a number of policies and measures to address both mitigation and adaptation and has a national action plan on climate change. And that national action plan has a large focus on energy efficiency. Next slide, please. So we have a document called Unlocking National Energy Efficiency Potential, which is a very detailed document created by the Government of India after contributions from many stakeholders involved. It gives directions in terms of how we can initiate energy efficiency process into a new system, whether it is the service sector or manufacturing sector, and at what stages you can have what kind of interventions and what kind of audit you can have, what kind of reviews you can have, and what kind of achievements you can realize at the end of it with all supporting green technologies involved. So we have a document which guides the future activity, and more and more industries and organizations are adopting this and improving the energy efficiency process within the corporation, contributing to the overall energy efficiency. So we have a well-defined process to guide us through this energy efficiency to unlock the energy efficiency potential in the organizations as well as in the country. Next. Some of the assumptions based which are used in this generating this document is the future technologies and innovations impacting energy efficiency. There are a lot of factors which are thoroughly discussed. Some of them are basically predicted what is likely to happen in 2022, 24, 27, 31, 45, 50, like that. There are long-term predictions, short-term predictions, and the technological developments which are likely to be a factor which will help in energy efficiency. And it's a very elaborate, detailed document which helps any organization to plan for energy efficiency from the beginning. Okay. Next.
Sir, last 5 minutes only, sir.
No, I think I'm through. Now we talked about we talked about sustainability. We talked about environmental effects and climate impact, and how energy efficiency basically is going to help us to achieve all these targets. And we also talked about international organizations putting goals and policy frameworks, nation itself defining its own document, a framework which helps everybody to contribute energy efficiency. But now whose responsibility is it? Who is involved in achieving energy and efficiency? It is everyone. Everyone has responsibility for energy awareness and energy efficiency in their work areas, and it is very, very, very important duty of every citizen, because the climate change is no more a possibility. It is already upon us, and our efforts today are going to define the sustenance of and well-being of human race on this planet. Okay. Thank you very much for hearing this. Any questions? Madam, I'm through.
Navya?
Yes, ma'am. I request participants, if you have any doubts, please ask. Shall I conclude, sir?
Yeah, you can go ahead.
Yeah, thank you, sir. On behalf of the organizers, I sincerely thank Dr. S. Sreenivasa Chary garu for the inspiring session on energy efficiency. Your insights into sustainable practices, innovative technologies, and efficient energy management have given us so much to think about. The research directions you highlighted, such as renewable energy integration, smart grids, AI driven energy management, and energy efficient computing, open exciting avenues for all of us to explore and contribute towards a greener and smarter future. Let us all take these ideas forward, not just as a knowledge, but as action, working towards to build a sustainable world where every watt counts. I once again thank Dr. Sreenivasa Chary garu for motivating and guiding us towards a brighter and energy efficient future. Thank you so much, sir.
Thank you, madam.
I also thank all the participants for your engagement and curiosity. Let us let us carry towards today's learning forward and come together again for tomorrow's session for exploring more ideas and more innovations. Thank you all. Feedback form will be forwarded. I request all of you to please fill the feedback form for the second session.